Hey everyone, today we're diving into an incredibly powerful tool for circuit analysis, the Fourier series. It's this amazing method for taking messy, complex, real-world signals and seeing the simple, elegant patterns that are hiding inside. Let's get right into it. So picture this. You're trying to figure out a circuit, but your input voltage isn't some nice, clean sine wave. Nope, it's something like this square wave. Now, all our usual tricks, like using phasors, they're fantastic for simple sine waves, but they kind of fall apart when you throw a signal like this at them. And let's be honest, signals like this are everywhere in the real world. These kinds of signals, the ones that are complex but repeat over and over, have a name. They're called periodic functions. And because they're not simple sine or cosine waves, our go-to AC analysis methods just don't seem to work. So that's the problem, right? How on earth do we predict what a circuit is going to do with such a complicated input? And here is the beautiful central idea. Instead of banging our heads against one ridiculously hard problem, we're going to do something much smarter. We're going to break it down into a whole bunch of easy problems we already know exactly how to solve. You can think of the Fourier series as being kind of like a prism for signals. You shine this complex wave, our square wave, through it, and it splits it apart into all of its basic components. It literally reveals the signal's secret recipe, showing you that this complicated shape is actually just a bunch of simple sine waves all added together. Okay, so here's the more formal definition. What the Fourier series tells us is that any periodic function, no matter how weird it looks, can be built using just three basic ingredients. First, a steady DC component. Second, a main sine wave at what we call the fundamental frequency. And third, a whole bunch of other sine and cosine waves that are integer multiples of that fundamental frequency. We call those multiples harmonics. So, you know what? Let's actually try it. Let's see if we can build that square wave from scratch. The first and most important ingredient is just a single sine wave that has the same frequency as the square wave we're trying to make. This is our foundation, our fundamental frequency. Okay, now watch what happens. We're going to add in another sine wave, but this one is at 3 times the frequency. That's the third harmonic, and it has a smaller amplitude. The second we add it in, look at that. The tops start to flatten out, and the sides get way steeper. The shape is already starting to change, big time. Now we add the fifth harmonic, and wow, it's getting even closer. You can see where this is going, right? If we kept on adding the odd harmonics, the 7th, the 9th, the 11th, and so on, we'd get closer and closer to a perfect square wave. And that's the whole point. A really complex wave is just a sum of simple ones. Okay, so we get the principle, but that brings up a really big question, doesn't it? For any signal, how do we find that exact recipe? How much of that third harmonic do we need? And what about the fifth? How do we figure out the precise amounts of each ingredient? Well, the answer is something called the Fourier coefficients. These are the actual numbers. We call them A sub 0 for the DC part, A sub n for all the cosine bits, and B sub n for the sine bits that tell us the exact amplitude of each ingredient in our recipe. Now, the way you find them involves calculus, specifically integrals. And I'm not going to lie, it can be a lot of tedious work. So, of course, the next question is there an easier way? Is there a shortcut? And thankfully, yes, there is. The absolute biggest time saver you have when you're doing Fourier analysis is taking advantage of a signal's symmetry. This right here can save you an unbelievable amount of work. If you look at your signal and see that it has even symmetry, boom, you instantly know that all the sine terms are 0. You don't have to calculate a single one. If it has odd symmetry, like our square wave did, then the DC term and all the cosine terms are 0. And if it has half-wave symmetry, the DC and all the even harmonics just disappear. Just by spotting the symmetry first, you can wipe out huge chunks of the calculation before you even start. All right, so let's say we've done it. We've got the recipe for our input signal. It's a DC value plus a whole collection of simple sine and cosine waves. So how do we actually use that to figure out what a circuit is going to do? The key, and this works as long as our circuit is linear, is a beautiful concept called the principle of superposition. This is the masterstroke that makes this whole technique possible. It means we can look at the circuit's response to each simple ingredient all by itself, and then, at the very end, just add all those individual responses up to get the final answer. So this gives us a really clear step-by-step game plan. Step 1, find the Fourier series of your input signal. Step 2,
Figure out how the circuit responds to just the DC part. Step 3, use your trusty phasor method to find the circuit's response to each and every harmonic, one by one. And this part is crucial if you're doing something like filter design. And finally, step 4, just add all of those results together. That's it. That's the whole method. Now, what's cool is that this method gives us more than just the output waveform. It also lets us understand 2 other really important things: how power gets delivered in the circuit, and what we might call the signal's frequency fingerprint. When we start talking about the average power in a circuit like this, there is one rule, one absolutely critical rule that you have to remember. And that rule is different frequencies do not mix. They stay in their own lanes. What does that actually mean? It means the voltage from the 3rd harmonic and the current from the 5th harmonic, they do not work together to produce any average power. None. So to get the total average power, it's actually beautifully simple. You just calculate the power from the DC part, then the power from the fundamental, then the power from the 3rd harmonic, and so on. And you just add them all up. Finally, wouldn't it be cool if we could actually see a signal's recipe? Well, we can. It's called a line spectrum. It's just a simple plot that shows you the amplitude and phase of every single harmonic component. It's a unique frequency fingerprint that tells you exactly what that signal is made of. And check this out. Here is the frequency fingerprint for that square wave we were building earlier. You can see it so clearly. There's a big component at the fundamental frequency, a smaller one at the 3rd harmonic, an even smaller one at the 5th, and absolutely nothing in between. We've literally turned a shape that exists in time into a map of frequencies. So we'll leave you with this final thought. We've been talking about this in terms of electrical signals, but this idea that complex, repeating things are really just a sum of simple sine waves, it applies almost everywhere. It's the foundation of how we synthesize music. It's how JPEG image compression works. It's how we analyze sound. So if all these complex things are built from such simple harmonic ingredients, what does that really tell us about the nature of the world around us?